No problem. I'm 15 degrees off. That's 1, 2, 3 lines. 3 times 3 is 9. 9 seconds. Go. And then all I'm using is my bank angles. So up front, you just have to memorize some very simple numbers, and it works. Now here's the cool thing. Trying to make everything that you teach a student actually pertinent. Okay? Everything that we teach, you can actually find a real reason or a situation in which it would help you. Jets turn at standard or half standard rate turn? Why?
Because of those speeds that it gets really steep bank.
If you're going 300 knots and you bank over, well, let's take it 15% at 300. It's going to be 30 and 15. That's going to be 45-degree bank. Anybody feel comfortable at 45 degrees in an RJ? Neither do the passengers. Okay? So in a jet, you're turning at a half standard rate turn anyway. If you get in and they have a turn coordinator, you'll notice that, what does it say? 4 minutes. So whenever you see a 4 minute, you know that that's a fast airplane. That's why it says 4 minutes. It's a half standard rate turn coordinator. Okay? Questions? There's something else. Now it's gone. Oh, I'm sorry. That was the relation. Guess what? This rule, 5 degrees equals 3 seconds, works in the airlines. I love the little stories. I've already heard like 2 back. One captain had no idea how to use a VOR receiver anymore because all he had done for the last, I don't know how many years, was use the FMS, and it just kind of flew for him. Had no idea how to use a VOR receiver when their FMS failed. And you know, the co-pilot's like, oh, I can do this. It's little stupid things like that that literally, can this knowledge actually help? Yeah, it actually can. There are situations. Are you going to use it every day of your life? No. But the more you know, the better decision you can make when you're actually in a situation. So anyway, that does transfer over to a jet if that helps anybody to want to remember it. Okay, that's compass and time turns. When you're doing partial panel tracking, you still use compass and time turns. What people start doing is trying, especially with the moving map, they start trying to follow the map or follow the numbers and do that. A GPS tells me where I was, not where I am. So it's always about three seconds behind you. In a turn, it can be as much as 5 seconds behind you. Because it's still trying to figure out where you just went. I'm in a turn. Oh, wait, oh, you're turning, you're changing. So it's very easy to tell when students start doing that. And I love it. I just read over and zoom the map way out. So they're like a little dot in the middle of the US. And all of a sudden they're like, I don't know what to do. All right, let's talk about it. Okay? So you got to be careful of that, especially with the G1000, that they're not using that map. So I had to turn it off on several students because that's all they were doing. Gyroscopic instruments. Do we have a gyroscopic instrument in the Diamond Star? Backup attitude indicator. So we still do have one, and if they go and fly anything else, they're probably going to be dealing with gyros. So let's talk about gyros real quick. Here's my gyro. My gyro can do really cool things, like balance on my finger. What's it called? Rigidity in space. So what is rigidity in space? How does it work? What principle? It's my awesome round circle. So I spin that around. What principle am I dealing with in rigidity in space?
Inertia.
I mean, I just put that thing on my finger and it was just like standing straight up. I totally can't do that if it's not spinning.
Gyroscopic precession.
That's what made it spin.
Is it the one
You notice
where
it kept on spinning around my hand? That was gyroscopic precession.
object in motion wants to stay in motion?
Oh, Mr. Newton. Yes, Mr. Newton said if an object's in motion, it wants to remain in motion in the direction in which it was going. So when you go around a corner and your sunglasses fly across the dashboard, what were they doing?
Actually, in the same line.
They were just trying to go in a straight line. car is what moved. They just kept on going in a straight line, and as the car moved, boom, they hit the side. So, if I took a snapshot of this spinning disc right now, of this point, which direction was it moving when I took that picture?
Straight up.
It was moving in that direction. It's attached to an arm, though, that now swings it. Okay? The resultant force, what do we call it? You go sit and get in the Gravitron at the county fair. Centrifugal force is what we call it. And that's why people say it's an imaginary force, and I'm not going to get into all that garbage. You can read all sorts of weird stuff on that. Centrifugal force is that force which acts 90 degrees to the plane of rotation in all directions. All that is the fact that that point's trying to go in a straight line and gets pulled around. Okay? How fast does a gyro in an airplane spin? How much? 18. 18 to 22,000 RPMs. Pretty fast? Pretty dang fast. So we calculated it out. I'd have to like do the math. If you want to sit down and do the math, we said, okay, the gyro in the airplane is probably about this big. Okay? If you measure that disc all the way around, you're looking at probably 1, 2, 3, 4, 5 inches probably in circumference. So that means it's traveling 5 inches times 18,000. That'll give you your inches, divide it out, figure it out, come down to feet, whatever. That thing's traveling, I can't remember the number now. We'll have to do it. What is it, 5 times 18?
90.
90,000? Divided by 12? Get out those phones. Come on. Technology savvy people. Divided by 12.
7,500.
7,500? 7,500. And that gives me what then?
That's feet per second.
That's feet per minute. So feet per minute. How many feet are in a mile?
5,680.
So that means I'm doing roughly 1.5 miles a minute, which is 90 miles an hour. If you take a car and smash it into a brick wall at 90 miles an hour, what's the G-force you're going to feel? Because that's what's happening to your gyro, is you're getting a centrifugal force equal to 90 mile an hour impact. It's equivalent to about 7 to 9 Gs depending on the gyro. Okay? So, think about that. I'm pulling 7 Gs in all directions. How much is gravity? 1 G. So when I held that on my finger, how much was pulling down on it? 1 G. How much was pulling straight up? 7, 7, 7, 7, 7, 7, 7. Well, that's easy math. I got plus 6 Gs in excess. What's going to win? The 6 Gs.
6 is bigger.
6 is bigger than 1. So I can put that in any attitude. I can put it on an angle, and it'll just sit on an angle. I can do anything with that, and it'll maintain its rigidity as long as I'm producing an excess amount of G-force. So that's all I'm doing is fighting that gravity. Make sense? Kind of. The way I like to, you can illustrate it. If we took, let's say we go down to good old Sam's Surplus Army Military Store and got a big parachute. And we get 10 sumo guys that all weigh 1,000 pounds. And they all grab the edge of that parachute. Okay, so I got 800 pounds all the way around it. And we throw Craig up here. Sorry, you're the smallest guy.
It's okay.
We throw Craig up there, what's going to happen?
Jump on like a trampoline.
Jump on it like a trampoline, it's not going to move. It's the same principle. I've got 7 Gs pulling in every direction, and I got 1 G of gravity bouncing around. Whatever. Okay? So, gyroscopic precession. How does gyroscopic precession work?
Gyros introduced to a force that reacts 90 degrees in the direction of the wind. resultant
They
force.
call it a phenomenon because no matter how slow or how fast you spin it, it happens 90 degrees.